a kind of situation like region 1 and region 2 and region 3. Okay. And here the wave is psi 1, and here the psi 2, here the wave psi 3. And the thickness of this is d. First, and then the barrier height here is V naught. And the electron energies tunneling, passing through this barrier, it has energy E, okay? And first, we have to think that the D is reasonably small so that the waves can pass through this region 2 and it reach to region 3. And obviously, in a general case where the D is reasonably small, then the psi 1 is going to be A e to the I kx plus B e to the minus I kx. The minus direction means it's reflected. So the electron wave in the region 1 consists of 2 tones, which one is propagating in a positive direction and the other is a negative direction. So this wave is actually the kind of wave deflected at edges. Here, let's say the x equals to 0. Okay, here the x equals to d. So psi 1 is going to have this, and then the k value is k1, something like that. Okay, and then this k1 is, according to our discussion last time, it should be over h bar. It is nothing but from the energy is h bar squared k squared over 2m, right? This is a momentum. P is equal to mv is equal to h bar k, right? So from here you just get the k, and then k is going to be written just like that. Okay, now the psi 2 also has the reflection at the x equal to d. It consists of 2 waves moving towards the positive direction, positive x, and the negative. K2x, something like that, right? And then here the K2 is square root of 2m E minus V naught over h bar. When energy is greater than, electron energy is greater than the barrier height. Okay? When the electron energy is less than the barrier height, it is going to be reflected, but some of the waves is going to penetrate to pass through. So in that case, this thing goes the other way around, but we're going to talk about that in a minute. Now, in the region 3, the wave side 3, okay? Since it's go to the infinity here in this direction is minus infinity, so there's no reflection in region 3. So in region 3, we're going to have a wave equation just moving toward the positive x, which is k1x. Okay? Now, this is the case where d is reasonably small. But what happens if d is large? When d is large, then we don't have reflections on this edge, x equal to d. So when d is large, we just have side 2 is going to be c to the e I k 2x only, right? When energy is bigger than electron energy is bigger than the barrier height. But when the electron energy is less than the barrier height, then the side 2 now becomes c e to the minus k 3x, something like that. And then here the k3 is going to be square root over 2m. Now v naught minus e in this case over h bar. Something like that. Okay, it can be arranged in this fashion. Then with this wave equations, we have each cases where first d is large and the second case where d is small, and when d is large, we can have the case where the electron energy is greater than the barrier height, and the second case is the electron energy is less than the barrier height. And when d is small, we can have the case where the electron energy is greater than the barrier height, and also in this case, we can have the case where the energy of the electron is less than the barrier height. For each 4 cases, we can get the transmission reflection coefficient. Reflection coefficient is going to be defined as the amplitude of incoming incident beam and the reflected beam. The amplitude of the 2 waves ratio is going to be called reflection coefficient. And the transmission coefficient, T, is nothing but 1 minus R. In other words, reflection coefficient plus the transmission coefficient should be 1 all the time. Okay? And then we have some peculiar case where the tunneling transmission coefficient. And this tunneling transmission coefficient is going to be defined as T as F over A amplitude of the wave side 3, okay, and amplitude of the electron wave, incoming electron wave A, this ratio is going to be tunneling transmission coefficient, something like this. Okay, this is the in the classical concept. This cannot be done. It cannot be calculated. The tunneling cannot happen if the incoming the energy of electron is less than the barrier height. Okay, but in this quantum theory, in other words, in the Schrödinger equation says if D is reasonably very narrow, very small, then some of the electrons of which energy is less than the barrier height can tunnel these barriers, and that's what happens in reality. Okay, and that kind of tunneling phenomenon cannot be explained in the classical theory, but can be explained in this Schrödinger equations, quantum approach. Okay, so the actual calculation of the transmission coefficients and reflection coefficients and are given on the text by using the continuity conditions, which means at the boundaries x equal to 0 or x equal to d, okay, the wave should have a single value. So psi 1 should be equal to psi 2 at x equal to 0. And the derivative of psi 1 with respect to the x should be equal to the derivative of psi 2 with respect to the x. That is the continuity conditions at x equal to 0 and x equal to d, both boundaries. This single value mathematically well-defined conditions has to be met. So using that, you can have all these coefficients. And tunneling transmission coefficient, derivation of a tunneling transmission coefficient is not given on the text. It's rather complicated, but it is possible to have that. So if you're really interested in that, you may have, you may spend some time to get those tunneling coefficients. It is possible to get that. A little bit complicated. Okay, so that is a review of particle in a box, Schrödinger equation, electron, matter wave. And today we're going to discuss about the linear harmonic oscillator. Okay, that is related to the atoms. Not the electrons. Again, I have to emphasize that the atoms can be considered as the oscillator because atom itself in a single crystal. We're always talking about the single crystal, right? The polycrystal or amorphous doesn't have any meaning. So, a single crystal solid. All the atoms are interrelated with the Coulombic force, bonding energies, something like this. You can be thought of this. Something like this, right? In the solid. And at each atom in the x and y and z directions, it is going to oscillate. oscillate, and the amplitude of this oscillation is related to the energies of this lattice atoms, like temperatures or light energies or whatever, okay? So depending on the temperature, for example, the amplitude of this oscillation is different, but we're talking about the case that this atom is not really displaced from its original positions, even though it is oscillating, okay? When you increase the temperature too high, of course, this atom is going to, the connection, bonding energy between these two atoms is going to be dislodged to make this whole thing a deformation, and then even further temperature is going to be met. There is a connection between the atoms, but it's not going to be regular in any sense. And even further, the bonding energy of the atoms is going to be isolated, and we call that gas, right? So the situation that we are talking here is that the oscillation of atoms in a solid state, and then that oscillation is in the elastic range, not inelastic range. So we are not talking about the very large energies. We are going to talk about these solid with shining light, okay? And then the shining light is not going to give huge energies to melt down the solid. It just have a delta E we are talking about here is about less than 1 electron volts, okay? So in this range, each atom can be thought as an oscillator. So linear harmonic oscillation, in understanding of a linear harmonic oscillation, is very closely related to the lattice atoms. In other words, the phonons, right? Linear harmonic oscillation. In the linear harmonic oscillations, or F equal to minus Gx, that is the spring constant. And like here, the G is kind of a thing that the F, which is MA in the Newtonian, right, is related to the Gx, something like this. So G is a force constant which can be related to the Newtonian just like this. And potential energy in this situation is going to be integration of the force, so that is Gx squared. And then that is m omega square x squared over 2. All right? Because omega, angular frequency, is nothing but G over m from classical theory. Natural frequency, we call this natural frequencies. Okay. So in a free electron case, this potential energy is nothing but 0. But in an oscillation, it is not 0 anymore. It is some values it has. So the Schrödinger equation now becomes time-independent Schrödinger equation is now going to look like this: h bar squared and E minus potential energy, and then that potential energy is going to be omega squared x squared over 2 and psi, the function, and then that is going to be the 0. And the solution of this, we are not going to solve this actually, but we do have a solution which is going to be something like alpha x squared over 2, where alpha squared is mg over h bar squared. And then fx is kind of a polynomial with some values if you look into the text. And so the eigenvalue of this equation is now going to be 1/2 h bar root g over m. And that is n plus 1/2 h bar omega. Now, the one thing you may notice is that n can be 0 for the ground state. n1, 2, 3, 4, something like this. So if you draw the eigenvalues of this harmonic oscillator case, the ground state and the first excited state is just half h bar omega. And then the next is going to be h bar omega, and then evenly distributed h bar omega. Okay? So this half h bar omega has a special meaning. We're going to discuss about this later, but in this harmonic oscillator case, n can have 0 for the ground state. That is a different thing. But most striking difference from the free electron is that we see the energy excited more and more than the energy gap between the allowed energies becomes large and large in a free electron case. But in a harmonic oscillator case, no matter how high it goes, it is excited, the next available energy is always h omega away from its state. So that is a very important thing you have to notice. So here you have some points to notice in the harmonic oscillator case. The 0 ground energy is 1/2 h bar omega. That is different from the classical theory. And the energy gap is evenly distributed and h bar omega.